how do we exist? For centuries, this has been a scientific mystery. Not exactly how we exist, but how anything exists. In particular, you might recognize this chart from high school chemistry or college chemistry, which tabulates all the different chemical elements that exist in the universe. But did you know that at the very, very beginning of the universe, right after the Big Bang, only two elements existed? Hydrogen and helium. Only two elements. And you know this is not true anymore, because if it were, you would not be possible. There's a lot of athletes in this room. What about the sodium in your sweat? What about the element that makes your blood red? Iron. What about when you smile, the calcium that lines your teeth? I don't know who I don't know who that is. What I'm saying is that you are not What I'm saying is you are not just hydrogen and helium, but made from all these different elements. So if there are only two elements that began in the universe, how do you exist? Where did all these different chemical elements come from? Turns out they did not originate on Earth. They didn't even originate within our own solar system. You see, for something that's so intimately related to our physical existence, it actually begins extremely far away. It begins here. Stars. The ones that dot our night sky, or the one that sits over our head during the day. So today's talk is going to be about how stars are responsible for creating the elements that allow us and everything we know to exist. So to begin, what do we think of when we think of our own sun? We think of something that's bright, it's hot, it's burning. That's why we have summers. But it wasn't always like this. Stars actually begin in some of the coldest and darkest regions of the universe. And the temperatures here tend to be like negative 430 degrees, much colder than our mornings in Berkeley. And in these cold regions, sometimes the dust that's floating around in these regions like to form a clump. And that clump is the catalyst for the birth of a new star. In particular, the star clump is floating around in dust clouds like these. And star clumps are massive, they're gigantic. And if it's massive, it has a lot of gravity. So if it's floating around in here, then it likes to pull in the dust, combine that dust into itself. It becomes more massive. It's more massive, it has more gravity, pulls that dust into itself, becomes more massive, gravity, pulls in more stuff, etc., until it becomes a full-blown star, at which the pressures of the star's mass on its center is so huge, it's so huge, that the temperature in the center goes up to 27 million degrees Fahrenheit. It's really hot. And this is the temperature at which nuclear reactions begin, in particular nuclear fusion. So this is different from nuclear fission. Nuclear fission is what the US used to bomb Japan. Nuclear fission takes a larger atom and it splits it into smaller ones. Nuclear fusion, which is what happens in the center of stars, it takes smaller atoms and combines them into bigger ones. And every time this reaction happens, a little extra energy is let off. And that extra energy goes into what we know as sunlight. So why is this important? Well, do you remember when I told you that the universe is only hydrogen and helium? It was actually mostly just hydrogen. That means stars are also just fusing mostly just hydrogen. Hydrogen is the smallest and simplest atom you can get. When you take two hydrogen atoms together and you smush them together, when you fuse them together, you add up their protons and you get a bigger atom. Not just a bigger atom, a new chemical element. So that our star is fusing all this hydrogen in the center. It gets a little ball of helium in the center. Now you have a helium center. Okay, what does it do with this? Well, the star wants to keep fusing. That's what it means for a star to live, is while it's fusing. So it takes the helium. It starts fusing the helium. You take the two heliums, you add all their protons together, you get a bigger atom, you get a new element, beryllium. So do you see what's happening here? We started off with just hydrogen. We took hydrogen atoms, we fused them into the next chemical element, helium. We take hydrogen and helium, we fuse them into even bigger elements. and bigger elements, going down the periodic table into bigger elements, all the way until we get to iron. Iron is when it becomes completely unfeasible for stars to fuse anymore. It just requires too much energy. So even though we began as 100% hydrogen, now if you cut a star in half at the end of its life, after it's been burning and fusing for billions of years, you'll see something that looks like this. So you have hydrogen, you get helium, you get a bigger element, and a bigger element, and you fuse into bigger elements, all the way up until iron. And this is called, by the astronomers, as the onion skin model, because it looks like an onion. Also, congratulations, you just witnessed chemical elements being created within the center of stars. And now you may be wondering, okay, so you have all these chemical elements inside the center of the star. How do they get out of the star to become the potato chips that we eat, to become the swimming pools that we swim in, athletes, to become the service dogs that love and protect us? How does this happen? Well, this is actually a really extremely complicated question, and to be honest, there's just not enough time to exactly describe how it goes from here to here. But I can summarize one crucial detail, and it only takes 2 words: star death. This is a galaxy. In case you didn't know, galaxies are these enormous structures in space of hundreds of billions of stars, many of which are like the stars that we described just earlier. And I'm going to show you what happens to this galaxy a little later in time. NASA has just captured a gigantic flash of light. A star, much more massive than our own sun, has just died in a catastrophic explosion called a supernova. And a supernova happens when it's no longer able to fuse. We saw that when it reached iron. It's no longer able to fuse, so it gravitationally collapses on itself. It rebounds, and it explodes. This is a concept illustration, it's not the real thing, but it's something like this, and it's crazy. It's a catastrophic explosion. And when all that debris settles after the explosion, we get these beautiful supernova remnants. So this is called the Crab Nebula. This is called the Cassiopeia A Nebula. And what you're basically looking at is the corpses of dead stars. All their mass has just been flung out and everything. So when a star dies, all those chemical elements that it's been stewing for billions and billions of years inside its center is thrown out, and it's redistributed into the chemical composition of the universe. This is including chemicals like carbon, like nitrogen, oxygen, phosphorus, chemical elements which are key to life. And this enables all those chemical elements to be available to form into those little clumps that we talked about, and those clumps can become suns, like we talked about, or solar systems. They can become planets, and eventually us. Oh, sorry. So if you think I'm insinuating that you're made out of a dead star, then you're absolutely right. You are the reincarnation of stars that have died a long time ago. And even though it's not completely clear, the story of how you got from here to you is not, it's a story for another time. The next time you look in the mirror, just remember that you're not a star in a figurative sense, but a literal one. Thank you.